Peter here with the physics of the particle model. So we're starting with heating processes, and we need to get clear about what we mean by the stuff that we're heating up. So what is matter? How do we understand it? Well, the particle model is a distinction from other models that were around many years ago, one of which was that matter is continuous. Doesn't matter how much you make it smaller and smaller, that it's going to look like the same stuff. Another one that was popular in the 19th century was that matter is made up of little energy vortices, like little tornadoes. Well, those two didn't survive, and the particle model was the winner. The idea that if you get down small enough, you find that there's distinct particles. Today we call them atoms, we call them molecules. So the particle model came out, and we know that that is the correct one now. We're going to have a look. They missed out. We're going to have a look at the particle model. We're going to go to a PhET simulator. So let me just click over here. Rightio. So here is a simulation of matter, and you can see that we're in a container. We've got some water, liquid water, and it's in this container here, so it's confined. It is at what temperature? Let's see, 286 Kelvin, in other words 13 degrees centigrade. So just go 286 minus 273 is the magic number, and you get the reading in centigrade. So there's a little blob of water just sitting there, and there we see the particle model. It's made of particles, made of molecules. We could look at other things that are just a single atom. So here's some liquid argon, which is very cold, minus 187 C. Normally argon is in gaseous form, you're breathing it, it's 1% of the atmosphere. Oxygen, which is a little diatomic molecule, and they've also got neon, which is monatomic also. So particles, atoms or molecules. You can see that it's the kinetic particle model, kinetic motion. Particles are in motion all the time. If we go to solid, here we are at negative 127 degrees C. The particles are still in motion. That's very cold ice there. You could go to this simulator, you could make it even colder, and the particles will still be moving. So constant motion, whether it be solid, liquid or gas. When it's in gaseous form, you can see the particles moving around, you can see them spinning. They don't simulate this, but there's actually jiggling within the molecule as well, so motion of the particles in that way. They're spreading out, filling up the whole container. This is what we expect from a gas. Whereas with a liquid, yes, still in motion, but now there's a bit of connection between the molecules. There's some bonds external to the particles. I'm not talking about the bond within the particle. I'm talking about bonds between particles, and that's kind of holding it in that shape of the water droplet. It's sort of filling up the container. Sort of, maybe not simulating that entirely. Maybe it's more like a drop of water sitting on top of a bench or something. But anyway, the usual thing you say in the particle theory is that water will fill the container it's in, just at the bottom of the container, takes the shape of the container. Whereas when you go to solid, that's like a piece of ice. So the particles are in a fixed location, the bonds are stronger. Strangely enough, we say that the kind of microscopic potential energy between the particles is lower there, and this has more potential energy. It has more potential to make a bond, whereas gas is the highest potential energy between molecules, so it has the most potential to form bonds and end up in a solid form like this, where it's a relatively strong bond. So there's the kinetic particle model, and constant motion, and you can see consequences for different amounts of bonding between particles with solid, liquid and gas. An interesting one that's part of the model, the theory, the particle theory, is that in the gaseous form there's lots of collisions, and the collisions are perfectly elastic, and that means there's no energy loss in the collisions. So the gas can just stay there forever and it doesn't eventually just sort of fall to the bottom of the container. It'll just keep on going when it's given that certain temperature, 156 degrees centigrade. So that's some steam that's been superheated beyond 100, and it will just keep bouncing around there, no energy loss in collisions. So there's the particle model. And coming back to our heading here, we do need to point out that conversion from Kelvin to centigrade. There's something you need to be able to do. Converting from temperature in degrees Kelvin to temperature in degrees centigrade. The offset is 273. So at 0 degrees centigrade, you'd add 273, and that's 273 Kelvin, so on. So you need to be familiar with using that conversion. So that's that one, and then now we've got some definitions that you need to be familiar with. I'll bring in, I went to the syllabus and I've dug out the actual definition from the syllabus. So let's have a look at these. There's 5 of these. It says that you will be able to, what does it say? It says you'll define and distinguish between these 5 definitions. So what have we got? Internal energy, add up all the potential energy and the kinetic energy of the particles in the system. The system's referring to how you've confined, or how you're yarding off the matter that's of interest. So we've got that bit of water there, we've got it in a container, so that's our system, and within that add up all the potential energy, all the kinetic energy, and you've got the internal energy. You will use the symbol capital U for internal energy. I think of it as like being universal. Universal means you're capturing the whole lot. It does, I just said that, but it's just capturing the microscopic energies. It's not capturing the macro energy, like if this container was moving at some speed through space. We're not worried about that. We're not really worried about gravitational potential energy. How far off the ground is it, and what potential? That's beyond what internal energy is about. Internal energy is about just within that piece of matter. What are all of the energies added up? We talked a lot, I'm going down to number 3 here, kinetic energy, which of course is about the energy with movement, but in particular when we're talking heat transfer, it's about motion of the particles in the substance. So we've already talked about that. Down to the last one, temperature. It's about, well, everybody knows what temperature is. How hot is it? The intensity of heat in a substance or an object. It's shown on a scale, so Celsius or centigrade, same thing. There's the Kelvin scale that we've looked at, and of course Fahrenheit's another one that's well known, and there have been others in history. It turns out that temperature is proportional to the average kinetic energy of the particles. So not potential energy, just the kinetic energy, and not like the fastest particle or the slowest one. On average, what's the kinetic energy of all the particles? That would be pretty hard to calculate. Imagine that's gas and the steam, all the particles zipping around. That would be hard to know. But that is another physics formula. That's not one you need to know, but it's interesting to see that there's a pretty firm connection between temperature and kinetic energy. Coming up here to heat, here's a precise scientific definition of heat. Energy transferred from one system to another because of temperature difference. Well, yes, that's not how we use heat normally. We in normal everyday language we talk about something having, a certain amount of heat within it, which isn't really the scientific one. Scientific is about energy transferring from one thing to another, and that transfer is what's known as heat. So it's a kind of a dynamic thing, something happening over time. The last one, thermal energy. Well, thermal means heat, so thermal energy is to do with that part of the internal energy which relates to the temperature, and temperature relates to the kinetic energy. And kinetic energy is about the motion of the particles. So they are interlinked, and that's why it says in the syllabus you will be able to define and distinguish. So spend a bit of time figuring out which is which. So that part which relates to the temperature, and then we go on kind of the next thing, we're going to go to the next video, is going to be about this formula where that amount of energy that caused a delta T, or a change in temperature, delta T, temperature changing in some way, is related to an amount of energy and also related to some mass, and then there's a constant that we'll talk about later. So there's 5 definitions. You need to be familiar with them. If your teacher likes you learning definitions, then learn them, but definitely be able to say, recognize them, say in a multi-choice question, say which one's which. So there's our definitions that we've done, and we're going to just have a quick talk about heat transfer. You need to be familiar with this idea that there's different ways that heat transfer can occur, and you've probably seen this before. So suppose you've got a saucepan, it's got some water in it, and we're heating it up, got a flame there, there's a few bubbles appearing, you can see a bit of vapor coming off, and heat transfer. So here's heat being transferred into the system of the saucepan. So we've got some radiant heat coming from that flame. So it's coming out. We can put our hand here. If you put a hand here, you could feel the radiation coming from that hot flame. So that's causing the metal of the saucepan to heat up, and then it's going into the water, so that's conducting from metal to water at that point. Between the two substances, metal into the water starts to move because the cold water kind of is a little more dense and can pushes the hot up, so you get this kind of circulation starting to happen where the warmer water starts to go up in the middle there, and the cooler drops at the sides, comes in to replace the hot, and around you go. So that's convection current, so a term you might have heard. First one was radiation, and convection, of course, and we mentioned conduction where the two materials touch. Also, if you been going for a while and you put your hand on the handle, you might feel a bit of conducted heat there as well. So conduction, touching substances; convection, motion of the substance being heated; and radiation, which doesn't need any substance, because if you stand in the sun on a hot day, you can just feel the radiant heat coming and the waves of energy coming at you, and that's travelled through space, so it didn't need a substance to heat up to get to you. It's just travelling through the vacuum of space and radiating energy, giving a heat transfer from the sun to you. So there we are. We've covered about the particle model, converting Kelvin and centigrade, some definitions, and methods of heat transfer.